At this point, we'll now discuss how we transform between various model types. We've already seen an example of how we go from a regular differential equation model to state space form, but we haven't yet discussed how to go back and forth between state space form and transfer function form. So to begin with, we'll look at beginning with a state space model and transforming it into a transfer function. Recognizing that state space form is really just a differential equation, we can basically find transfer functions in the same manner that we've done previously, because when we found transfer functions in the past, we begin with a differential equation model. So the first step when we find a transfer function is to define what's the input and what's the output. By default, that's sort of already done for us. In the state space form, u is the input and y is the output. The next step is then to take the Laplace transform, assuming zero initial conditions. So we'll take the Laplace transform of this first equation, the state equations. Here we have a time derivative that becomes multiplication by s in the Laplace domain. Okay, and so here we're a little loose with the notation, but this x dot is a vector of time functions. And then over here, we get a vector of Laplace functions, x of s. A is just a constant, so it can come out front. The time function vector becomes a vector of Laplace functions. B is just a constant, and then this vector of time-based inputs becomes a vector of Laplace functions again. Doing the same thing with the second equation, the vector y becomes a vector y of s, c is a constant, vector x of s, d is a constant, vector u of s. So once we've taken the Laplace transform, assuming zero initial conditions, we then need to rearrange our equations into the form output over input. So we want to find y of s divided by u of s. If you look at these equations, we explicitly have y and u, our input and our output, but we have another variable x, which is the internal state of the system, which is neither the input nor the output. And so what we need to do is we need to eliminate x of s from between these two equations. If I call the first equation 1 and the second equation 2, what we'll do is we'll solve 1 for x of s. Okay, so we've got two x of s terms. I'm going to subtract the a times x of s to the other side to get them together. So I have s times x of s minus a times x of s. I can then factor the x of s out. And so when we do this, we need to be a little careful. So number one, matrix multiplication does not commute. The order of multiplication matters. So a times x is a different thing than x times a. And so since x is multiplying a on the right-hand side, when we factor it out, we need to keep it on the right-hand side. Furthermore, looking at this, s is a scalar and a is a matrix. So in order for this subtraction to make sense, we need to multiply s by the identity matrix I of the same dimension as a. So that constitutes one side of our equation when we subtract the a times x of s. On the right-hand side of that equality, we're still left with b times u of s. Okay. Then we need to finish solving for x of s. If this equation was a scalar equation, all we would do is we would divide through by this factor, divide through by this quantity. In this case, however, this is not a scalar, it's a matrix, so we can't just divide through. What we need to do is to multiply by the inverse of this matrix. In particular, so we want to cancel out that si minus a, so we multiply on the left-hand side by its inverse. We have to do that on both sides. Okay, and so the product of these two inverses is then just the identity matrix. And so in essence, they cancel out, just leaving us with x of s. So this is an expression for x of s. We then take that expression for x of s and substitute it into the second equation. And so looking at this, we have y of s is equal to c times x of s, where x of s is equal to this whole expression. Okay. So then we have eliminated x of s. We're just left with our output y and our input u. And then the last thing we need to do is to just get it into the form output over input, y over u. So we can factor out u of s on the right-hand side, and then divide the u of s to the left-hand side. So that notation isn't entirely correct. If we have a single input, single output system where u is a scalar and y is a scalar, then this is absolutely correct. If we multiply out our matrices in this manner, we'll get a single transfer function with y as the output and u as the input. In the case that we have multiple inputs and multiple outputs, then u of s and y of s are vectors, and you technically can't divide through like that. However, if you do this multiplication, if you do execute this expression as it's written, what you will end up with is you will end up with a matrix of transfer functions. So however many inputs and outputs you have, the product you'll have that product in number of transfer functions. So if you had 2 inputs and 3 outputs, you would have 6 different combinations of inputs and outputs, giving you a matrix with 6 elements. Okay, so that's the sort of the end result, the punchline for how we go from transfer function form to state space form. If I gave you the A, B, C, and D matrix of a system, you could then give me what the corresponding transfer functions are. Let's go ahead and illustrate this with an example. Okay, so here's our A, B, C, and D matrix. We will determine a transfer function following the equation we found on the previous slide. The C matrix times the quantity of the S of S times the identity matrix minus the A matrix. You invert that whole thing, multiply it by the B matrix, and add the D matrix to it. So in this case, our C matrix is a row 1, 0. We'll have a scalar I times a 2 by 2 identity matrix. So the identity matrix would just be 1, 0, 0, 1. When you multiply it by the S, you'll get an S0, 0, S. You subtract off the A matrix. You invert that whole thing, multiply it by the B matrix, and add the D matrix. So doing this subtraction internally here, you just subtract the individual elements of the 2 matrices. So in the upper left, we have an S. In the upper left, we have a 0. So S minus 0 is S. 0 minus 1 is negative 1. 0 minus 2 is negative 2. And S minus negative 3 is S plus 3. We want to invert that whole thing. If you don't recall how to invert matrices, really quickly I'll show you how to do a 2 by 2. So if we had elements A, B, C, and D, the way you invert it is that you switch the terms on the diagonal. So you swap the D and the A, and then you change the sign of the terms on the off diagonal, and then you divide by the determinant of the matrix, where the determinant is A times D minus B times C. Okay. More generally, the inverse of a matrix is equal to its adjoint divided by its determinant. We won't get into that, but just to jog your memory a little bit. So in order to invert this 2 by 2, we're going to swap the terms on the diagonal. So the s plus 3 comes up here, the s goes down, and then we change the sign on the off diagonals. So the -1 becomes a +1, the -2 becomes a +2. Then we divide by the determinant. We multiply on the axis s times the quantity s plus 3, and subtract the product on the other diagonal, the off diagonal -2 times -1. Okay. Then we multiply out. So I'll go ahead and take this denominator out front. I have, if I distribute this, s squared plus 3s, and then subtracting a +2. And then I'm left with the C matrix multiplying this matrix multiplying the B matrix. So I'll just go ahead and do it in steps. I'll do these two first. I multiply this row by this column, multiply a 1 by the s plus 3, 0 by the 2. So I end up with s plus 3. Then I take the same row, multiply it by the next column. I get 1 times 1 and 0 times s. And then finally, I take this row and multiply it by that last column. I'll get s plus 3. And I still have the same denominator out front. So that concludes that example. We went from a state space form to a transfer function form. A couple of things that we'll point out real quickly. So in this case, we had a single input, single output system. We could tell that we had a single input because we had only one column in our B matrix. We had a single output because we only had one row in our C matrix. If we had multiple inputs and multiple outputs, we could have multiple columns in our B matrix and multiple rows in our C matrix. And when we execute this expression, instead of ending up with a single transfer function, we end up with a matrix of transfer functions. The ability of a state space form to model a system with multiple inputs and multiple outputs in a compact manner is one of its advantages. If we had 2 inputs and 3 outputs, we just have one set of A, B, C, and D matrices as opposed to 6 transfer functions. It turns out when you get into controller design and things like that, the computation of the controller is also relatively simpler. Something to point out is this denominator defining the poles in the system corresponds to the determinant of this matrix. When we inverted this matrix, its determinant is what resulted in the denominator of our transfer function. And so this is something that I'm going to come back to on the next slide. As I stated on the previous slide, the solution of this equation, the determinant of si minus a equal to 0, became the denominator of our transfer function. And so the solution of this equation it gives us the poles of our transfer function. If you think back to some math classes you've had, you might recognize something like this as providing the eigenvalues of a matrix. So the solution of this equation is equivalent to finding the eigenvalues of A. And so this is a sort of an interesting result. Looking back at the previous example, where these were our this was our state space model and this was the resulting transfer function model. Sort of something interesting to look at is if you look at the state space matrices, it may not be as sort of apparent what some of the dynamics of the system are. You know, just looking at the A matrix, it may not be as easy to see what the poles are as when you look at the transfer function, though there is a nice relationship here. Beyond that, you can't see what the zeros are immediately at all. And when you have a multi-input, multi-output system, the notion of what the zeros of the system are becomes rather challenging. That's not something we're going to get into, but it's something to keep in the back of your mind a little bit about what some of the advantages and disadvantages of the relative modeling approaches are. So in the previous slide, we went from state space form to transfer function form. Here, we're briefly going to mention how we go in the other direction from transfer function to state space. So the state space form is not unique. This is something we mentioned previously, but there are in essence an infinite number of choices of state variables. The transfer function is unique though. So no matter which A, B, C, and D matrix you start with, if it's for the same physical system, you will end up with the same transfer function. The other way is not the same though. And so what you'll generally do is you'll pick sort of a standard form, what we call a canonical form, that makes the mathematics simple. So here's one example from earlier in the module. We had a differential equation earlier at the very beginning. This is its transfer function representation, where u is the input and x dot is the output. So this is the resulting transfer function. When we took that differential equation and put it into state space form, this is what we got. And so what you'll notice is that these terms in our state space model correspond to the coefficients of the denominator. And then our C matrix corresponds to the coefficients of the numerator. And so this is one of our standard forms that I mentioned. It's what's called controllable canonical form. And just by inspecting the coefficients of the numerator and the coefficients of the denominator, you can put the system into controllable canonical form. It turns out that this form is mathematically efficient for calculating state feedback controllers or for determining a property called controllability. There's another form that's called observable canonical form that is convenient mathematically for calculating observers or estimators. There's even another form where you can basically decouple each of the state equations. So you could end up with an A matrix that's a diagonal matrix where x1 dot is only a function of x, x2 dot is only a function of x2, and x3 dot is only a function of x3. So there are several different forms out there that are chosen because they're mathematically nice. When you do that, you can oftentimes end up with state variables that have no physical meaning. You can end up with a state variable that's 2 times the position plus 3 times the velocity, some nonsense. But it's a convenient choice because it makes the math simple. It makes the calculations efficient and computationally inexpensive.